Greetings. My name is Dr. Machibiza with the African Center for Global Health Innovation and Research. So today we are going to look at stoichiometry. Right. So the prerequisites for our stoichiometry, students should have covered the introduction to chemistry and the chemical bonding module. Students should appreciate the various types of bonding, ionic bonding, covalent bonding, and dative or coordinate bonding. Students should also be comfortable with unit conversions and basic mathematics involving atoms, grams, moles, and units of volume. So this is our periodic table. So like I always say in our modules, students should be able to know by heart the first 20 elements of the periodic table. Right. So stoichiometry, ladies and gentlemen, is the study of the quantities of reactants and products in a chemical reaction. So the word came from the Greek words stoichion, which means element, and metron, which means measure. So basically, we are measuring elements. So we've got three fundamental laws which govern our stoichiometry. The first being the law of conservation of mass. The mass of the products is always equal to the mass of the reactants. Secondly, the law of multiple proportions. The mass of one element combines with a fixed mass of another element in a ratio of whole numbers. Thirdly, the law of constant composition. All samples of a given chemical compound have the same elemental composition. So why is stoichiometry important? Stoichiometry is important because it allows a deep understanding of chemistry, as it allows students to, one, predict how much of a reactant participates in a chemical reaction. Secondly, it also allows students to predict how much product is going to be obtained. And lastly, how much reactant might be left over, if any. So we then come to the mole. 1 mole of a substance contains 6.022 times 10 to the power of 23 particles. And that number, 6.022 times 10 to the power of 23 particles, is what we call the Avogadro's number. And from the Avogadro's number, we then come to two important formulae in as far as the mole. Secondly, the number of moles is equal to the concentration times the volume. So these two formulae are very, very important in as far as the calculations involving the moles are concerned. Chemical formula of ionic compounds. So as we know from our bonding module, we saw that ionic bonding gives rise to ionic compounds, and we have got examples of ionic compounds. The examples of ionic compounds which we remember from the bonding module, we've got sodium chloride, we've got magnesium chloride, we also have got calcium chloride, calcium oxide, and potassium chloride. So in chemistry, stoichiometry in particular, it is very, very important for us to be able to balance equations. It's very, very important for us to be able to balance equations. And for us to balance equations, we need to use our three laws as we have shown in the previous slide. So we are now going to try and work out or balance these equations. Sodium plus chlorine to give us sodium chloride, magnesium plus oxygen to give us magnesium oxide, magnesium plus chlorine to give us magnesium chloride, and potassium plus chlorine to give us potassium chloride. Lastly, calcium plus chlorine to give us calcium chloride. Right. So we now want to try and balance our equations. Okay, the first one, we have got sodium plus chlorine to give sodium chloride. Right. So when we are balancing our equations, ladies and gentlemen, we should ensure that the number of atoms for the reactants should always be equal to the number of atoms for the products. Okay, so if we look here, we've got 2 chlorine atoms, but here we only have got 1 chlorine atom. So for us to be able to balance these 2 chlorine atoms, we then need to ensure that we write a 2 here. Okay, if we write a 2 here, we now have 2 chlorine atoms on the right hand side, and we have got 2 chlorine atoms on the left hand side. Right. When we look at sodium, we have got 2 sodium atoms on the right hand side, but on the left hand side, we only have got 1 sodium atom. So for us to balance this equation, it means we now need to put a 2 here. So when we do this, we would have balanced the equation. Okay, right. Let's go to the next one. Magnesium oxide. Magnesium plus oxygen. Okay, to give us magnesium oxide. Right. So with this one, we have got 1 magnesium atom on the left hand side, 1 magnesium atom on the right hand side. So in as far as magnesium is concerned, it is a balanced equation. For this one, we've got 1 oxygen atom on the left hand side, 1 oxygen atom on the right hand side, meaning that this equation is balanced. Okay, so for now, we are mostly concentrated with writing balanced equations. Okay, we are not yet looking at writing the states of these atoms. Okay, for example, sodium is a solid, chlorine is a gas, the resultant sodium chloride, it's a solid. For now, we are not yet concerned with the states of these atoms and compounds. Okay, we are mostly interested in balancing the equations. Right, let us proceed. Magnesium plus chlorine. Magnesium plus chlorine to give us magnesium chloride. Okay, right. So if we look at this one, here we have got 1 atom of magnesium and we have got 1 atom of magnesium here. Okay, here we have 2 atoms of chlorine, meaning that we also need to have 2 atoms of chlorine on the left hand side. Okay, then we have got potassium plus chlorine, okay, to give us potassium chloride. Right. So we know that chlorine exists as a diatomic molecule, right? So when we look at potassium on the reaction side, which is the left-hand side, we've got 1 potassium atom. When we look at the product side, we've got 1 potassium atom. But if we look at chlorine now, we've got 2 chlorine atoms on the left-hand side, but only 1 on the right-hand side. Meaning for us to be able to balance this, we put a 2 here, okay? Chlorine is balanced, but potassium is not yet balanced. So what do? We need to put a 2 here for potassium to ensure that the equation is balanced. Okay. Then we have got calcium plus chlorine, okay, to give us calcium chloride. Okay. Calcium plus chlorine to give us calcium chloride. If we consider calcium, we've got one calcium atom on the left-hand side, one calcium atom to the right-hand side. We have got two chlorine atoms on the left-hand side and two chlorine atoms on the right-hand side. So this equation is balanced. Okay. So when we are balancing ionic compounds, it's very simple and easy. But for now, we now want to proceed to balance covalent compounds. Right, so we are going to rub the board and then we try to look at balancing covalent compounds. Right. So balancing equations, ladies and gentlemen, is very, very important for chemists, okay? Because whenever you write your chemical equations, they should be balanced, right? So when we are looking at now covalent compounds, for example, we've got hydrogen plus oxygen. We know that these gases, they exist as diatoms, okay? So hydrogen plus oxygen, okay? For us to get water, okay? Hydrogen plus oxygen for us to get water, right? If we look at hydrogen here, okay? If we look at hydrogen here, we've got two atoms of hydrogen on the left-hand side. We've got two atoms of hydrogen on the right-hand side. In as far as hydrogen is concerned, it is balanced. If we look at oxygen, we've got two atoms of oxygen on the left-hand side and one atom of oxygen on the right-hand side, meaning that this equation is not balanced. So for us to balance this equation, we need to put a 2 here, okay? If we put a 2 here, it means we now have two oxygen atoms on the right-hand side, which is the product side, okay? And we also have two oxygen atoms on the left-hand side, which is the reactant side. But when we look at hydrogen now, we have got two hydrogen atoms here, but here we've got four hydrogen atoms. So for us to have four hydrogen atoms here, we need to put a 2 here, and we would have balanced our equation. Right, let us continue. Carbon, okay, plus oxygen. We know that oxygen exists as a diatomic molecule, right? And carbon plus oxygen, we always get what? Carbon dioxide, right? So when we look at carbon atoms, one on the left-hand side, one on the right-hand side, it's balanced in as far as carbon is concerned. When we look at oxygen, we have got two oxygen atoms on the left-hand side and two oxygen atoms on the right-hand side, meaning that it is also balanced, okay? Right, now let us look at nitrogen plus hydrogen to give us ammonia, NH3, right? We know that nitrogen is a gas. It exists as a diatomic molecule. Hydrogen is also a gas. It exists as a diatomic molecule, right? Di means two, okay? Right, so if we look now at the number of nitrogen atoms, we've got two here, but you've got only one here. So for us to balance the nitrogen atoms, it means we need to put a 2 here, right? So when you look at the left-hand side, we've got two nitrogen atoms and two nitrogen atoms on the right-hand side as well. But when we consider the hydrogen atoms, we have got 6, 2 times 3 for hydrogen, okay, which is 6 hydrogen atoms. So for us to have 6 hydrogen atoms here, it means we need to put a 3 here, right? So when we do this, we would have balanced our equation. Right, let us proceed. Right. We now want to look at isotopes, okay? After we've balanced our equations, we've seen how we balance both equations for covalent compounds and equations for ionic compounds, right? So from the balancing of equations, we now want to proceed to isotopes, okay? If you remember from our bonding lecture, okay, when we spoke about isotopes, we said that isotopes are different atoms of the same element with the same atomic numbers, which is the number of protons, but different mass numbers due to differences in the numbers of neutrons. We gave examples of chlorine 37 and chlorine 35. We also have got carbon 14 and carbon 12. Okay, so there are many elements which exist as isotopes. Right. So for us to be able to calculate the atomic number or the relative atomic mass of a substance, okay, which exists as isotopes, we basically say the atomic mass of isotope 1 times its percentage abundance plus the atomic mass of isotope 2 times its percentage abundance. Okay. Uh, when we do that now, we'll be able to come up with a relative atomic mass of an element which exists as isotopes. Right. Sometimes you're expected to calculate the relative atomic mass from percentage abundance. So from what we have been saying, for both carbon 12 and carbon 13, as well as chlorine 35 and chlorine 37, when you have got now the percentage abundances, it's basically saying the atomic mass of isotope 1 times its percentage abundance plus the atomic mass of isotope 2 times its percentage abundance, right? So that sum is going to give you the relative atomic mass of the element. Right. Let us now see an example for chlorine. Given that chlorine 35 is a percentage abundance of 75%, and chlorine 37 is a percentage abundance of 25%, calculate its relative atomic mass. So from the formula which we have stated previously, we know that the relative atomic mass is equal to the atomic mass of chlorine 35 times the percentage abundance of chlorine 35 plus the atomic mass of chlorine 37 times the percentage abundance of chlorine 37, right? So that sum now is going to give you the relative atomic mass. So the reason why the relative atomic mass of chlorine is 35.5 is because it is a result of this calculation from its respective isotopes. Okay, the isotope which we are namely chlorine 37 and chlorine 35. So whenever you are given abundances, percentage abundances of the isotopes, okay, you can always calculate the relative atomic mass. Right. We now move on to the empirical formula from mass. Right. What is the empirical formula? So basically, the empirical formula is the simplest whole number ratio of atoms which are present in a given compound or a molecule. When, for example, we look at ethane, okay, which is represented by C2H6, the ratio of carbon to hydrogen is in the ratio of 1:3. And it can be written simply as CH3. So CH3 will be the empirical formula or the simple whole number ratio for ethane. Right. Sometimes we may be asked to calculate the empirical formula of a compound. Let us look at the example as projected. Find the empirical formula of an oxide of magnesium consisting of 0.32 grams of oxygen and 0.96 grams of magnesium. Right. So for you to be able to calculate the empirical formula, you need first to identify the atomic masses. Right. So we know that the atomic mass of magnesium is 24. The atomic mass of oxygen is 16. So for us now to find the empirical formula, we first have to find the number of moles of the two elements, right? Since we are given that there is 0.32 grams of oxygen and 0.96 grams of magnesium, the number of moles for magnesium is going to be equal to the mass of magnesium divided by the atomic mass of magnesium. And from the question, the mass of magnesium is 0.96 grams, okay? 0.96 grams is projected here, divided by the atomic mass of magnesium, which is our 24. So we have got 0.04 moles of magnesium. We also do likewise for oxygen. We are given that the mass of oxygen is 0.32 grams, and we know that the atomic mass of oxygen is 16. So therefore, the number of moles of oxygen is going to be 0.32 divided by 16, which is 0.02. Right. So for us to find the simple whole number ratio now, we need to divide the moles by the smallest number. And as we can see, 0.04 and 0.02 moles, right? If we divide by 0.02 here, we get 1. If we divide by 0.02 here, we get 2. Meaning they are in the ratio, the oxygen and magnesium are in the ratio of 1:2. Okay? Therefore, the empirical formula is going to be 2 magnesium, is going to be magnesium, oxygen 1, and then 2 oxygen atoms. Okay? They're in the ratio of 1:2. Okay? They're in the ratio of 1:2. Okay? Right. Let us proceed. When we consider now sulfur and oxygen, okay, which form sulfur dioxide, we are given that an oxide of sulfur consists of 40% sulfur and 60% oxygen. And we know that the atomic mass of sulfur is 32 and the atomic mass of oxygen is 16. So the composition usually adds up to what? Up to 100%. Right. So the question is requiring us to find the empirical formula for sulfur dioxide. Right. So first of all, we are going to say the percentage composition, okay, of sulfur divided by the atomic mass of sulfur, which is the percentage composition of sulfur according to the equation is 40%. We are going to divide it now with the atomic mass of oxygen, which is 32, and we are going to get 1.25 moles. Similarly, we do the same for oxygen. We are given that the percentage composition of oxygen is 60%, okay? We are going to divide it with the atomic mass of oxygen, which is 32, and we are going to get 3.75 moles, right? So after we've obtained the number of moles, we then divide by the simplest, we divide by the lowest number, which in this case is 1.25. 1.25 divided by 1.25, we get 1. And 3.75 divided by 1.25, we get 3. So we are going to get 1 sulfur atom, 2, 3 oxygen atoms as the empirical formula. We now also have what is called the molecular formula, which indicates the actual number of atoms present in a compound. Remember, we said the empirical formula represents a simple whole number ratio of the atoms which are present in a compound or a molecule. But when we look now at the molecular formula, it tells us the actual number of atoms which are present. Right. So, being given the molecular mass of a molecule or a compound, the molecular formula could be calculated using its empirical formula. Right. So let us look at the following example. A compound has an empirical formula of CH2 and a molecular mass of 42 grams per mole. Find this molecular formula. Right. So first things first, okay? The empirical formula of the compound X, okay, is equal to the molecular formula, right? As we know, the empirical formula is the simplest whole number ratio of a compound, right? So the molecular formula, it actually shows us the number of atoms which are present in the compound. So the empirical formula times a number n always gives us the molecular formula. Okay, so n becomes the multiplying factor, right? Since we are given that the formula of the compound is CH2, we now know that CH2 times N, which is a whole number or a multiplying factor, which is multiplying our empirical formula to give us our molecular formula. Okay, CH2 times N is going to be equal to 42 grams per mole. Okay, since we know that we have got carbon, the atomic mass of carbon is 12. Okay. We also know that we have got hydrogen. The atomic number of hydrogen is 2. Therefore, the molecular mass of this molecule is 12 plus 2, which is 14. Therefore, we are going to say 42 grams, okay, divided by the MR, which is 14, is going to give us N, the multiplying factor. As we simplify the equation, we are then left with 14N is equal to 42, and N is equal to 3. This therefore means we are going to multiply the empirical formula by 3 for us to get the molecular formula. So our molecular formula is going to be C3H6, okay? And this is propene. Right. We now look at what is called the molar gas volume. At room temperature and pressure, 1 mole of a gas occupies 24 dm cubed. Okay, 24 decimeter cubed. Deci 10 to the minus 1. Right. At standard temperature and pressure, 1 mole of a gas occupies 22.4 dm cubed. Okay, right. So the volume is always given by moles times molar gas volume. And we know that 1 mole of any gas at room temperature occupies 24 dm cubed, and 1 mole of any gas at standard temperature and pressure, it occupies 22.4 dm cubed. So these are very, very important in as far as calculations involving gases are concerned. And it's also important for us to state the standard temperature and pressure conditions. Okay, standard temperature and pressure conditions, we've got a temperature of 0 degrees Celsius and the pressure of 1 atmosphere. Room temperature and pressure, we've got a temperature of 25 degrees Celsius and the pressure of 1 atmosphere. Right. We now move on to the molar gas volumes. For us to be able to explain qualitatively the molar gas volumes, we need to know the laws which apply to gases. So the first one is the Boyle's law. Boyle's law states that the volume of a gas is inversely proportional to its pressure, provided the temperature is constant. Okay? When you look at Charles' law, it says that the volume of a gas is directly proportional to its temperature, provided the pressure is constant. When we look at Gay-Lussac's law, okay, it states that the temperature of a gas is inversely proportional to its pressure. Okay, right. When we look at the Avogadro's law, the volume of a gas is directly proportional to the number of moles of gas present, provided the pressure and the temperature are constant. So when we look at the three laws, the Boyle's law, the Charles law, the Gay-Lussac's law, and the Avogadro's law, it will then lead us to what is called the ideal gas equation. The ideal gas equation is PV is equal to nRT. Okay? Povo, not right, for those who like acronyms. Right. So for this one, our P is our pressure, V is the volume of the gas, N the number of moles, and R the ideal gas constant, which is given as 8.314 joules per mole Kelvin. And the temperature, take note, the temperature is measured in kelvins. This means that if your temperature is given as degrees Celsius, you need to convert the temperature into kelvins. And we know that 0 degrees Celsius is equal to how many kelvins? 273 kelvins. This means that a temperature of 100 degrees Celsius is going to be 100 plus 273, which is 373 kelvins. So whenever you get this ideal gas equation as a question whereby you are asked it or you require to use the ideal gas equation, always ensure that your temperature is in kelvins, because the SI unit of temperature is kelvins, right? If you are given the temperature is degrees Celsius, ensure that you convert the degrees Celsius into kelvins. And also take note of the units of R, which is the ideal gas constant. Sometimes it can be given as joules per mole per Kelvin. Okay, you should ensure that the units which are given are always in line or in sync with the units which are given in the question. So if you do that, you'll be able to tackle any questions requiring you to work out the required volume or requiring you to work out the pressure in this ideal gas equation. Right. So there is a variation of this ideal gas equation. Remember, in our earlier slides, we said the number of moles can be given by mass over mR. So sometimes you may be asked to calculate the mass, okay, of a gas required, right? So what you do is, for this n, which is the number of moles, you can then substitute this n, the number of moles, by mass over mR. Okay, you can substitute it by mass over mR, and then you'll be able to calculate the mass of the gas required. The mR, you can always obtain that from the what? From the periodic table. So thank you very much. We have reached the end of our lesson, stoichiometry, the balancing of equations, the gas laws, the Charles law, the Boyle's law, the Gay-Lussac's law, and the Avogadro's law, which gives us now what we call the ideal gas equation, PV is equal to nRT. So, ladies and gentlemen, it's very, very important that we practice these questions. Chemistry is like mathematics. Without practice, you won't be able to tackle the questions. So practice as many questions as possible. The concepts we have already given you, and you need to practice. As you know, practice makes perfect. So stoichiometry is not difficult at all. It only requires you to practice the questions so that when they come in an exam, you'll be able to tackle them perfectly well. So thank you very much, and enjoy your studies in as far as chemistry is concerned. Bye-bye.